going. So Alicia has all the time to tell us about what she does that's exciting and new. It's my pleasure to introduce today Dr. Alicia Kinoshita, who is a associate professor in the Department of Civil Construction and Environmental Engineering. Her work lies in the intersection of civil and environmental engineering, looking at hydrology. And she is, from what I gather, a true California native, at least academically, as far as I can tell, in the sense she got all her degrees in California from University of uh, California at Los Angeles, and though did a postdoc at Colorado, wanted the mountains, I assume. She does some very interesting work in looking at watersheds, and so she's going to talk about it. She also is now the director of undergraduate research at San Diego State University. So in addition to being a professor, a PI for research, she also has places additional. So with that, I'd like to welcome Alicia to the CSRC Colloquium, and we look forward to hearing more about your work, Alicia.
Thank you, Sachi. That was such a nice introduction. Stole a little bit of my thunder from my slides, but that's okay. I'll repeat it. There we go. All right. Well, I'm excited to kind of share what we've been up to in my research group and sort of the projects that we're working on. So just to kind of get us started here, I'll be talking about ecohydrologic recovery and runoff predictions after fire in Southern California. So I wanted to start with this image, super relevant considering we are all currently in California or San Diego area. So this is actually a satellite image, and I think August 24th, 2020. So you can see there's like over 650 wildfires that are blazing in this image. You can see the little red blobs here, and then the smoke coming off of all of these fires. So we had a massive fire season, and it's actually still going. I think a few of them are contained, but they're not out yet. Okay. So I know Sachi already just introduced me. Yes, I did all of my degrees at UCLA. I spent a couple years over at the Colorado School of Mines, and then now I made my way back to California, which is close to home, so really enjoy being here. This is just an image of me in my favorite office, which is being outside and collecting field data, and then obviously taking diligent notes there. So I enjoy camping, hiking, traveling. So my research is able to take me outside, and that's really why I love doing what I do. Oops. All right, so none of my work is really possible without a great team. So you're only as good as your team. So I always like to take a minute just to acknowledge all of the awesome students that work with me in my lab. So currently I have several thesis students who are working on some pretty cool projects in urban areas and also wildfires, and doing some different modeling projects. So we try to keep them funded and interested and engaged with cool colleagues and collaborators. As Sachi kind of mentioned, I'm also really excited about undergraduates and their participation in my work. So down here on the bottom, you can see I've got a couple students who are participating on one of my NSF my grants as through an internship type of program with our lab, and they're about 1 year. And then I'm also working with a student who I'm co-mentoring with, a JPL scientist. So it's really exciting times. Okay, so what do we do? So just a little bit about kind of my research group and our lab here is that we seek to understand changes that are following natural and human disturbances. So just kind of take a look at this panel of images here. This top one, you should all kind of recognize it if you've ever been to the Fashion Valley Mall. This is just the parking structure that's right next to the San Diego River, and it's designed to flood. This is a little culvert that's kind of cluttered right next to the campus as well. This is Alvarado Court, where all the cars are flooded for students and research foundation staff maybe and researchers whose cars got flooded. This is actually from a fire when I was working on in Colorado, and then this is just in our backyard, some invasive grasses. So we're trying to understand these changes that are happening to our water and the soil and the plants, especially with this kind of like our own human interactions? And then can we predict how everything is changing after disturbance, ultimately so that we can provide better management tools and resources, right? Okay, so just a little bit of an overview of what we'll talk about today. So we'll talk about some motivation, wildfires, and their impacts, because I'm not sure how familiar this audience is with all of that. I guess you can flag me down if it's too much. And then we'll talk about some prediction work that we've been doing, and ultimately kind of the recovery, so how long we need to try to understand these processes for, and then just a few sort of concluding remarks. All right. So I just want to kind of set the scene here. So we have these yearly occurrences of extreme events. So these have been increasing in cost since 1980, maybe, when they've been looking at this data set, and it's exceeded over $1 million or over $1 trillion. And this is not even all the way up to date. So this is only up to like 2018 when I put together this slide. So for me, I'm really interested in this sort of wildfire section, because it really dramatically alters the landscape. And then immediately following a wildfire are these impacts to our water quantity and quality. And so I'll kind of describe that. And both of these have significant implications for what's kind of happening downstream. Oops, wrong way, sorry. Oops, yeah, there you go. Okay, so this extreme events, they're kind of recognized across different disciplines. So while all of my degrees are in civil engineering, I'd like to identify often with being a hydrologist and a water resource person, so heavily water-based. And these extreme events, they're recognized not just in one discipline, right? Like they're recognized across many different disciplines, and they have lots of different facets that we need to try to understand, right? So I like this figure from this McPhillips paper, in that it kind of shows this transdisciplinary framework that's needed to conceptualize all of these extreme events, right? So you've got an extreme event, there's the event or the hazard or the disturbance, the fire, right? Or some sort of urbanization or tornado, and then it causes an impact, right? And then there's a corresponding response. So how we respond then kind of creates this sort of feedback between that extreme event and the impact, or between the impact and then kind of a subsequent response. So how we manage and adapt to the disaster kind of changes how the landscape may respond. So with that in mind, there's sort of this, all of these different disciplines that are represented and need to be kind of communicating with each other. And that's what I find exciting, is that I like to branch out and try all these different sort of collaborations with other people who are experts in other fields, like social scientists and geography and geology, things like that. So here's a slide just to kind of get us a little bit more acquainted with wildfires, since I think it's really important, since we're all here at San Diego State in California, that we kind of understand what's going on. So I made this slide originally. I used to make these just to kind of give us a sense of what's going on. I started doing this way back in my graduate studies, and used to be I didn't have to change the slide that often. Maybe 2000, 2007, all those big fire years. So the last time I made this was in 2018, and that's where you can see this orange glowing photo. And I left that in there because it's a really important reminder. This is the Camp Fire, and this is the town of Paradise. So about 2 years, right? That was one of our deadliest. That was California. That was actually at that time the deadliest and most destructive fire in our history. So like 159,000 acres burned, over 85 fatalities, 10,000 structures were destroyed. And then afterwards, they had to deal with their water. So they actually, EPA had to put out these announcements that you couldn't, like a do not drink from the tap. So, there's a lot of implications for these fires. And so I kind of left that one in, because they're natural oftentimes in California, and yet we're kind of at conflict with our own communities and such. So just a little bit about this year, which is just out of this world. We've got the August complex, which is still burning. Last time I checked, I mean, it's mostly contained, but there's still a couple spots. That is the largest, it's over 1 million acres, 935 structures destroyed. There's also the North Complex, and then the Glass Fire. Maybe some people get excited about that one because it was burning wine country, and nobody wants that. So there's a lot of these kind of famous fires that we're hearing about, and that are really getting a lot of attention. Okay. So CAL FIRE puts out these different lists. There's largest fires, there's most destructive, there's deadliest. And so you'll notice that those fires that I just kind of mentioned, they're appearing in our top 20. But also important to notice that in San Diego, we've got about 3 on that top 20 list for the largest fires in California. I didn't even show deadliest and most destructive, but Cedar Fire and Witch Fire, for those of you who are around in like the mid 2000s, might recognize those ones as well. So super destructive. And I think there were about 4 fires in the most deadliest category from San Diego as well. So our stats aren't super. Right? And if that's not alarming enough, yeah, we've got these future projections. And that's just that these warmer temperatures are being predicted. We've got earlier, meaning kind of like earlier snow melt, right? So we're gonna have these drier conditions, drier soils, and everything is then just kind of pointing to these longer fire seasons or larger areas burned. And it can become quite catastrophic, especially in California, where, you know, our fire season is immediately followed by our winter season. So just to kind of give you, get this where we're headed. So we can kind of look at this pre and post fire landscape, right? So in this top little cartoon here, this is just trying to depict it's just trying to depict an unburned surface. And so we have the vegetation sort of on the top, and then if you have rainfall, the water falls to the surface. It can either make its way through surface flow into the channel, or it can infiltrate into the subsurface. And then of course, all of these plants, probably when it's not raining, are transpiring. So we have an evapotranspiration or evaporation component, okay? So when we have a fire, what happens is the fire comes through and it completely changes the structure. So we have this acute loss of vegetation, decreased soil cohesion. So that means, you know, all of us have probably played in the dirt before. A lot of times it's a little sticky, right? It sticks together. What happens when we have a fire, oftentimes if it's burned too much, right? If it's burned at a high severity, it can become really ashy and powdery, kind of like a baking flour. You can think of it like that. So this decreased kind of soil cohesion, there's ash layer decomposition, and all of these kind of also create this hydrophobic layer that forms right on the surface of the soil, preventing infiltration right after the fire. Sometimes kind of seals the surface there. And that has some hydrologic consequences that I'm interested in. So, you know, there's decreased infiltration, there's decreased evaporation, so we don't have any more trees. And then that leads to these increased erosion and overland flow, flooding, the things that we're seeing in the news, all of these debris flows, and maybe things that we're not seeing in the news, like dry season flow. So in addition to some of these post-fire water quantity, geomorphology type of changes, there's also implications that come with that. So things like your water quality can be impacted, biotic systems, and also vegetation starts to come back. And so, you know, is it invasive? Is it not invasive? Different kinds of things that we can go into there. I always like to point out this little picture here on the most right. It's actually a fish kill. So those fish have been smothered by debris flow. So kind of traumatic there. But yeah, so there's all of these different changes, and it's central to my research and my motivating questions, which are, you know, what are the downstream risks and benefits, and how long do these last? Because not everything is kind of death and destruction, right? We do have this kind of rejuvenation and recovery, like this nice little, I think it's a cucumber, wild cucumber plant that kind of grows back. And then there's also this delivery of sediment and additional nutrients and nourishment to the system. So sometimes that's actually needed. But then we also, you know, as an engineer or policymaker, you might want to know how much water and sediment to expect and where and when to expect it. And so that kind of leads to what are the management implications. And then what are the controlling factors of that recovery? And what are the complex interactions between these post-fire hazards, recovery, and just kind of society, right? So I used to have an image of this guy who's standing in front of his house, and there's just this debris flow or this mud flow that's just going down his front, like right in front of his front door. And he's, in my mind, thinking like, oh my God, when is this going to stop? So I think, we have to kind of think about that interaction, complex interaction between society, the ecosystems, and kind of those natural processes. Oops, go ahead. So to answer all of those questions, the research methods that I use is a combination of field work, remote sensing, statistical analyses, and modeling. And so we'll be touching on just a little bit of the field work. I might mention it, but we'll be going a little bit more into some of the remote sensing and geospatial products, and then the statistical analyses today. Okay, so just gonna wrap up some of this background. So after a fire, what we find is that there's more water and there's more soil, just to put it really simply. So in this graphic, here's my mouse. In this graphic, this is, just notice that this is a long-term time series. So it goes from like about the 2000s until it's about a decade, let's say. And so each time you see these black inverted bars, those represent rainfall. And then all the clusters of those, these are sort of like seasonal rainfall. So you can almost think of these as every year. And with some of that rainfall, you have a corresponding runoff process or stream flow, right? So water comes into a control volume and then it's leaving. And so you see that's kind of seasonal, and that makes sense. We have rain in our sort of, what's our rain season, October through April-ish or something. And so we get rainfall, and then we get these higher flow events. Maybe if it's a really wet year, then we have a larger response. But what most of the literature says, and what's pretty consistent, is that after a fire, and that's denoted here with this dashed vertical line, is that's when that was when there was a fire. And so for this particular watershed that I'm providing as an example, it was 100% burned. And what everyone, the consensus is that you have this rainfall event, and then you have these huge peak flows. And so just one of these peaks, it's probably this second or third one, is this, kind of translates to this in real life. So I was standing here. Don't worry, I wasn't there when the bridge topped, but I was there when it was pretty close to topping out. So you can see kind of that debris and that mud up here, and the sediment laden flow had actually topped over this bridge. And then one of the things that I was interested in about a decade ago, I guess now, was that in these little black dots through the center, that's the average. Oh no, it's mad at me. Go back, wasn't done talking. Okay, that we have this vegetation. This is a representation of an average vegetation for this control volume, and it's kind of showing that cyclical or seasonal pattern that vegetation typically would show. But when it's all burned, that's when we're kind of seeing these larger stream flow responses, and I showed that statistically that there's the correlation there, and at the time that was somewhat novel. Okay. So I like to show this little squiggly lines plot as well, because I think this is also very important background for the project that I'm going to discuss, and predicting these peak flow values and tools for our water emergency response teams, right? So I like to call this like a spaghetti plot, but it's actually called a flow duration curve. So every single squiggly line here represents 1 year's worth of stream flow data. Okay, so when you look at these gray lines, that just means that it was a pre-fire years, before the fire event. And it's the amount of stream flow every single day and its probability that it's going to be exceeded. So what that means is that the 90% here, that means it's a higher probability that it's not going to, or a higher probability of its occurrence. So these are our low flow events. So every day if you go out hiking and you check the creek, that's your probability is going to be much higher that you're going to have these lower flows. Whereas during the winter time, when when we're having our storm events, we're gonna have this lower probability of a very large stream flow event. Okay, so that's kind of how you can read it. And the reason why these little squigglies kind of drop off is because in our Southern California systems, our watersheds, not all of them are flowing year round. So we have these ephemeral systems. And so that's what the drop off is kind of representing, that a lot of these channels are only flowing in the winter when they're getting rain. So the big kind of takeaway from this was that, these pink lines are the post-fire flow duration curves. And so for about 10 years, there's about 10 of these pink ones. These are elevated, and that system goes from being ephemeral to perennial. So that means it's flowing year round. So yeah, I like to point that out because I think that has really important implications for the ecosystem. And if you think about that, water resources, because we're in a water limited region. So it's kind of nice to think about having this excess amount of water. So in fact, it translates to about 750,000 gallons of water per year for nearly a decade after fires. And so kind of looked at that statistically for a few watersheds in Southern California. So I thought that was pretty amazing to note. And then the last thing to note here is for the project that we'll be talking about today, we're going to be kind of focusing on these peak flow events and looking at, how do we predict what's going to happen immediately after the fire. Okay, so one other thing that we need to think about to and start to understand in terms of process, because it's very important to me that we understand the process before we try to start to model anything, and so we can kind of just validate what we're actually producing, is we also need to take into consideration the soils and the plants. Okay, so the last process that I want to talk about here is this. So you've got this kind of hill slope here, and then imagine that this blue part here, that's the water, it's the channels running into our screen. So we have this vegetation, and what it does in Southern California, these kind of chaparral or shrub, and you can see what it looks like realistically, and it looks kind of nice here, but it's terrible to walk through. It's kind of thorny, but it kind of acts as these dams, and it traps sediment behind it, and so it kind of holds on to it. So only a little bit of it is going to start to make its way to the channel, right? Now, if we burn the surface and we burn the vegetation is no longer there to provide the service of damming the sediment. And so we see that the sediment starts to make its way down to the channel, where usually it's a little bit flatter, and so it just kind of likes to hang out there. And we call this sediment transport downslope as a dry ravel process. And so here, here's what an unburned slope looks like, and then this really nice contrast. This is the station fire in 2010. This unburned, oh man, I don't know why my finger. There you go. This unburned area there. And so lots of dry ravel process right after the fire when there's no vegetation to hold things back. And it starts to look like this. So we have this dry ravel deposit, which is hangs out down by the bottom of the channel, and it's just poised and ready to be transported downstream. And that's why we're seeing these really heavy sediment laden flows and debris flows. So one of the projects that we worked on to kind of monitor this and try to understand the process was in the Santa Monica Mountains. And so you can imagine I'm standing here in the channel, and I'm looking up the channel, and there's these big boulders. And so if you're in hydraulics or you know anything about physics, you understand that if you have water flowing down the channel and you have all this roughness in it, it's going to help to dissipate the energy. So it starts to form these kind of step pools. And then with subsequent storms, you start to move that dry ravel, and it starts to deposit within the channel itself. So this is just after one or two different storm events. And we were out there one time, and I think people walked by and asked us if this was the road, because it becomes so flat and smooth from all of that sediment. And we had to tell them, no, in fact, it's actually the channel that you're standing in, the stream channel. And we showed this for very long stretches. This was very unique form of geomorphology that we performed using terrestrial laser scanning, which is a form of remote sensing, where we looked at the elevational profiles at like the centimeter resolution, and all of these little black lines here, these are the contours, and so it's kind of showing the elevations. And what this shows is that after kind of a year when we've had all of our storm events come through, it really smoothed out the entire inside of this channel. Right? So it's totally obliterated any sort of step pools, any sort of energy dissipating mechanisms. And that's, again, a reason why we're seeing these large flows and large sediment laden and debris flows, okay? And then finally, all of that, I like to bring in that it impacts our water quality. So there's significant water quality impacts as well. So I'm not going to explain this graph in detail, but essentially you have that storm that's liberating all of that deposits and it's moving it downstream. And then within all of that sediment, a lot of times we have all of this deposition of pollutants and contaminants. And so in this colorful graph here, the blues are representing pre-fire samples and the reds are representing our post-fire samples. And these are just various metals that we were following before and after the fire, and each bar represents a different storm event that we camped out and grabbed our samples from. And then on the y-axis here is the event mean concentration. So, this is on a log scale. So these are, these are huge changes in our pre-fire metal concentrations in our water versus our post-fire. So this is just kind of an important concept to relate back to the physical changes in our landscape. All right. Oh, okay. Sorry. Getting ahead. All right. So where does that all lead us? So we were approached by CAL FIRE, some guys at CAL FIRE and the California Department of Conservation, and it's a really cool project to work on. And so this image here is the Holy Fire, and we're looking out. You can see Lake Elsinore there in the background. We're looking out on this burned landscape from 2018, roughly 20,000 acres or so were burned here. But after the fires come, right, we want to figure out, well, how much water do we predict is going to come, barreling down these watersheds, and which watersheds are going to be the ones that are prone to the most change and disaster, and are there values and assets, infrastructure that are kind of at risk. And so right after a fire, if it's large enough, these burned area emergency response teams, or BEAR, and watershed emergency response team, WERT, I guess, they go out, and this consists of engineers, hydrologists, geologists, and all kinds of GIS specialists. Sometimes they have archaeologists, and they have to assess all of the values at risk, and then they also do some modeling to figure out, to prove and predict what the volume is and what they can expect, and publish some recommendations in terms of mitigation. And they have to do this within about 2 weeks, right? Because you can't just sit on the decision. You have to start deciding how many K-rails to put in and how many sandbags and things like that, to kind of help protect some of the values at risk. So in the bottom right corner here is good old Row Countryman's story from 1949. And people chuckle, but this is actually still used in the post-fire assessment by CAL FIRE, California Department of Conservation, Forest Service. And there's a lot of reasons for this. It's a lookup table. It's empirically based, and it's a lookup table concept. So you find your watershed, there's about 250 of these, and you can look it up, and based on all this empirical evidence, you can find out what the volume or what the peak flow is for that watershed. And you can do some calculations based on some of its burn severity. But this is from 1949, so there's likely some error. So the CAL FIRE and California Department of Conservation came to us and said, we're interested in reassessing this methodology. And this resulted in the focus of one of my students, Brent Wilder, who's here today. That's great. And he also received a Joint Fire Science Program GRIN Award. So it's really awesome that we were able to work on this. And so this is like the latest and greatest of coming out of our lab right now. So the goals of this project were to predict post-fire peak runoff. Okay, so we wanted to look at all these small watersheds, because they were saying, hey, RCS, we're not really sure if it's working that great. And especially in these small watersheds, there's a lot of uncertainty. So that's what we wanted to test. And the hard part is finding data, right? How do you validate these models? And you have to kind of wait for it to happen. So we had to kind of do a huge inventory of what's available for us to do that. And we came up with 33 small watersheds that we could look at unburned and burned conditions with the Row Countryman's story. spoiler alert, didn't work out too good. So we wanted to apply machine learning techniques to post-fire hydrology. And as a disclaimer, you know, remote or machine learning has been around forever, but it's super novel in our field, and especially in this sort of application for post-fire risk assessment. So we use that to kind of identify some critical watershed parameters and then develop 3 tools that they can decide to use. Okay. So the study area consists of this range from all the way from San Diego all the way up to the Las Pajas National Forest. The color coding just represents different types of ecosystems and kind of their different locations. And the important takeaway is that a lot of these are within our transverse ranges and peninsular ranges in Southern California. So it's got this really granitic, decomposing granite characteristic, which is kind of why we're seeing a lot of our debris flow and sediment laden flows, right? So it's really, our geology here is quite unique. Okay, and then for the data. So we collected daily streamflow data, which I think you got an introduction to, where you saw the long-term time series, you saw the flow duration curves. And then we also collected hourly precipitation. Now that one's a little more tricky because, you know, some people have 15-minute data, some people only have daily. So finding, you know, the right amount of information to put into these models and to test is challenging. So just put that out there. And then, so there's a lot of hard work on Brent's part. And then there's, for each watershed, what we wanted to look at is like which parameters are really the controlling ones, which ones, you know, can we use to predict what's actually happening. So we came up with a not exhaustive list of 45 watershed parameters, and I'm sure there's tons more out there. And so some of the data sets that we use, so this is a burn map. So it kind of gives us an idea of high, moderate, low burn severities. A DEM is a digital elevation map from which we can derive things like the watershed area, the slope, perimeters, slope aspect, things like that. And then the soils, that gives us an idea of sort of the infiltration rates and capacities and soil behavior, things like that. And what we wanted to use was, because, you know, those Bayer teams and things like that, it needs to be kind of a quick assessment too, right? And we also want people to be able to use this. So we're using local, regional, and national databases. Everything can just be found open access. And then we use that to develop our random forest models. And then one other note is that some of these data sets, as they're kind of newer and more novel, especially since 1949, not all of them were going to be available for post-fire events. And specifically, I'm looking at this burn severity map. So that's really not available to us until maybe the late 80s, but even then they're kind of spotty, and so it is difficult for us to get that representation if we're trying to use watersheds where we have excellent stream flow runoff responses and data sets from like 1960s, right? So there's this trade-off between the data that we want to use and the data that we need. Okay. So the methods for this study, we first did a flood frequency analysis where we first used the row country minutes story lookup tables. So that's pretty easy. You looked it up, and then 1 year, 2 year, 3 years after fire, and it gives you some values. Then to kind of validate this model and our random forest models, we took observed data. So these are nationally gauged stream gauging stations where you can go online and download the data. And we took statistical distributions of the observed daily data. And from there, we were able to take out what's the likelihood of a 2-year or 10-year event. And so that gives us kind of the amount of water per time that we would expect for, you know, every 2 years that would happen, or a 10-year event would mean that it shouldn't happen as often, right? And those are the years that are usually focused on by these emergency assessment teams for a variety of reasons, but one of them being that we know that the 100-year events, for example, they don't happen as often, and also we don't have 100, you know, it's spotty, the 100-year records, 1,000-year records that we have. So statistically speaking, those are going to be more unreliable. So that's how we kind of validate that those two models. And then for the post-fire analysis, now this is interesting, right? So those flow duration curves, we didn't want to pick out what's the probability of the flooding event, 20 years later, because as the system starts to recover, the response starts to attenuate. So what we did was we kind of constrained that post-fire period that we grabbed our observations from. So we were looking within like 2 to 7 years, which is the standard time that we found in the literature for vegetation recovery. Okay. And then, like I said, I gave you the spoiler alert, RCS doesn't do so great. So we then wanted to look at random forests. We thought this would be a good method to create some models. So we trained regression models, and we created 2 random forest models. A 45, one with all 45 watershed characteristics for the 33 watersheds, which then allowed us to augment it to 74 samples, because we were able to say, well, in those 33 watersheds, they all had about maybe 1 to 3 storms that had adequate amounts of data. So that helped us to augment the number of observations that we had. And that allowed us to build this model for all of these different sort of parameters and different predictors. One of the main advantages of the random forest was, and why we chose it, was because of reproducibility. And then the feature's importance was sort of easier for us to interpret directly from the model, which then allowed us to conclude the impact of the different watershed parameters on the output or the peak flow that we're trying to predict. But there is a common issue when building the random forest model. There's just this tendency for overfitting, meaning that the variance can become a little bit too small. And so to address that, we actually reduced the number of features in our random forest. So we went from 45 to 5. So that's why we have the 2 different kind of options there, 2 different flavors. Okay, so in this figure below, this kind of is just a nice way to highlight that methodology. So first we created and calibrated the random forest with 45 parameters, and we'll call this RF45. We created 200 independent trees, and that's just kind of based on the trade-off for computational efficiency and accuracy. And then we took in all the samples, 1 through the 74 as input, and then each tree then classified each node condition to the 45 predictors to arrive at a prediction value for the independent trees. And then these independent predictions were averaged together to output a final peak flow, which is ultimately what we're trying to predict better, right, improve. So we come up with the peak flow, and then we compare that to our statistical observation from the observed flow to decide whether or not it performed well. And then finally, we developed a third model, which was just a simple 3-dimensional polynomial function for comparison. All right, so now to the good stuff. All right, so the RCS performance. So the pre-fire peak flow stream flows yielded a small bias, slightly like 0.16, and we do this in cubic meters per second, or cubic meters per second per kilometer squared. So we're normalizing it by the square area of the watershed. And this is just because we have large watersheds, we have smaller watersheds, so want to make it a fair comparison. And that's not shown on the slide, the pre-fire comparison. What we do show is this post-fire condition. So here we have the predicted response on the y-axis, and then the observed response on the x-axis. Okay, and all what this is really showing, if you're going to get one thing out of this, so RCS Q2 is the 2-year event, the 5-year event, and then just for some completeness, we put in the 10 and 25. But there's significant under predicting for the 2, 5, and 10-year events for most of the watersheds. And what we're seeing, you notice they're kind of just like all lined up here along the bottom. So it's showing that RCS method lacks sensitivity for small watersheds after fire. So there's generally this negative bias, and that's not super great, especially when I want to draw your attention to this red circle here, especially when you're trying to predict events like this panel of images here. So this large event here, we saw errors that ranged up to 1,720% during the floods at Dickey Canyon following that holy fire. So I know it's super blurry. We pulled a still from a video, but this is this channel here being completely flooded and it actually overtops, right? So this caused significant damage downstream. Okay, so what we did is we demonstrated that RCS overgeneralized the watershed processes, and it doesn't really adequately represent the spatial and temporal variability in the systems affected by fire and extreme weather events. I think there were some pretty big storms out there. Okay, so what's going on with RCS, right? So although it's commonly used, large inaccuracies exist, and this could be due to a multitude of factors, including watershed morphology, the exclusion of soil burn severity, these vegetation processes, and greater development in our wildland-urban interface since the development of this RCS in 1949. Okay. And then these RCS regressions were also developed for flows with low sediment concentrations. So imagine you have like clear water and then there's kind of a range, right? So as you start adding in that soil that was deposited on your channel, it's getting thicker and thicker, or hyper concentrated, as we would call it. So we would have these higher concentrations of sediment in it, all the way up to, like, you know, you can be up to 60% sediment by volume, right? So if that's not being taken into account in the RCS method. So since sediment bulking is implicit, we expect that there's going to be errors, because it's, you know, the model's independent variables that are strongly linked to the sediment production, they're not being used within that model, okay? So what we think is needed is that there should be this prediction of post-fire stream flow that's going to include things like burn severity and things like vegetation, which we know are controlling sort of factors on that peak flow occurrence. Okay, so I kind of want to end that with, well, stationarity is dead with our water management. So this very interesting paper came out and basically saying that a lot of our older hydrologic understanding, or understanding of these processes, is changing, right? So, you know, things that were developed in 1940s, the climate is different, the urban development is different. We have newer technology, newer understandings of our landscape. And so we need to start updating our tools and our process to predict. Okay, so that all leads us to this random forest model. So we created the two models, right? So there was the random forest 45, and you may or may not be able to see it on your screen, but these are the 45 different parameters. And then this is indicated by the more positive you get, the importance of it. Okay. And then the black lines are just the 5 most significant parameters. And so we then, after we had our random forest 45, we, you know, you can look at the R squared here. It's about 0.27. So that's not a great predictive model. And then there's an error of about 15.52 cubic meters per second of water per area, right? So, and that's for our RCS. And then, sorry, excuse me, the random forest is about 0.79. So it improves from the RCS, and it slightly decreases the root mean squared area. But what we were concerned about is that overfitting, right? Because it's 45 parameters. So of course, this method is going to try to fit it in the best that it can, right? And so I think we talked about that risk of overfitting. And so at that risk, we dove into the literature and thought about, you know, what parameters are really important and what have people shown. And so we came up with 5 parameters that were selected. So the 5 most important that the model selected. So days elapsed since the end of the fire to the storm, the area of the watershed burned, the watershed area to begin with, the perimeter, and the peak hour rainfall intensity. And that lowered the R squared, and it also kind of increased our error here. So, you know, obviously there's kind of still a lot to do here in terms of finding the right fit. And like we said, not an exhaustive list, and there's still a lot of work that can be done here. And part of this paper, which is not accepted, but has minor revisions, really minor revisions. So we're excited about that. But we're going to publish our data sets. And so that's something where people can augment it with their own observations. Maybe they've got some experimental watersheds where they can actually create a lot better or better trained models. Okay, so the third tool that was developed was a regression model. So we just used a 3D polynomial, and we took what we felt was the most important out of the 45 parameters that we had, and that was the area and the I-60. So in the literature, the intensity is always shown to be really important, the intensity of the precipitation. So if you've got a really slow storm, not many things are going to move, but as you increase the rainfall intensity, then we might start to see flashier systems. Okay, so that's what this is showing. Is it's just kind of showing the surface, and then all of these little black dots here, these are our observed flows. And with this tool, felt we had a predictive value of about 0.82 and a root mean squared error of 6.59. So out of the three models, we thought this one was the best for predicting peak stream flows 1 year after fire for small watersheds that were moderately burned. And insider scoop, our collaborators actually used this on the Apple fire. So if any of you are familiar with the Apple fire that was burning near Riverside, they tried to apply that. So kind of waiting till this is published before they use it a bit more. So that's exciting. Okay, so I kind of want to wrap up here with the 2018 Holy Fire, because we have a collaborator who has really awesome data available there in terms of rainfall and runoff. And as you saw, from that random forest and from our regression tools, we're limited by some of the data and the information that we have, right? So we want to start to explore how we can improve our prediction, our ability to predict. And we hypothesize that things like our burn severity, which is a controlling factor on that soil composition and how burned the vegetation is really important. So we want to use the Holy Fire here to kind of demonstrate that. And I know I already mentioned the Holy Fire, so I won't spend too much time on that, but this burned in Riverside County and it affected a lot of people. Records amount of rainfall fell. You can look down in this bottom image here, and this is just a huge sediment laden flows that are just kind of coming through, debris flows out of the Holy Fire area. Lots of people had to be evacuated, and I can tell you that Real Countrymen and Story definitely underpredicted, right? So we didn't want to leave the Forest Service or the CAL FIRE guys hanging. We wanted to be able to provide them with some sort of a tool. So recall that the earlier slide with our Dickey Canyon, where I was also showing some of that hyperconcentrated flows causing damage, right? We really want to be able to predict this a little bit better. So we're going to use the Holy Fire here as a case study to kind of highlight some directions that we can go with our newer technology. And for me, I'm really excited by the prospect of satellite-based remote sensing information to estimate ecohydrologic conditions. So just a refresher from our grade school days, you have these vegetation and they're kind of transpiring. You can have evaporation off the surface. So if you think about a water balance, you have water coming in through precipitation, and it can only leave in a few different ways. And that's going to be through evaporation, through infiltration to the subsurface, or by runoff, which is what we're trying to predict. This is kind of a nice photo of a channel in the Holy Fire there. Okay, so really believing that this vegetation is a huge factor that is a really hard variable to estimate in hydrology. You can't just go out there and put a thermometer out and measure it, or stand there and measure it. So it becomes really difficult. It's kind of one of these unknown values that we're always trying to understand. And so earlier on, we used to try to apply enhanced vegetation index, which is just an estimate of the biomass or the amount of vegetation present. And these are different satellite products. So you can see that we've got this moderate resolution imagery, which is at about 250 meters every 8 days. There's Landsat products that are 30 meters and 8 days. And these are just based on basically how how vegetation is reflecting. So you've got like vegetation typically reflects in green, so we can use the combination of those reflectances, these row near infrared, row red, and then some correction factors for the soil and atmosphere to estimate how much vegetation is present. Now, the resolution on these are, 250 versus 30. They're not, we know that vegetation varies on a much finer scale. So a new exciting product that's coming out is the eco stress, evapotranspiration, and evaporative stress index. And so that's kind of what we'll show in the next few slides here. So like I said, previous studies, we've shown that there's this correlation between the vegetation and when that stream flow is recovering. We've also tried to look at evapotranspiration, but the fact that I can see all of these different pixels means that it's not a high enough resolution. We can get some general trends as to vegetation recovering and varying with respect to how burned it is, but it's not enough information to help us get to where we want to be in terms of predicting our peak flow events. Okay, so I'll start to conclude here with the holy fire, which has a really nice setup where we can look at different watersheds within it. So this is Coldwater Creek, and then we have what we call a paired watershed. And so in this paired watershed, we have the opportunity to look at a burned versus unburned system. So we started using these higher resolution, these satellite-based imagery to look at vegetation, and so that's what the sum is, right? So we know that vegetation varies over, day one, and if the satellite's passing over again in 16 days, maybe that little weed has died off or something. So we like to take kind of a cumulative approach and look at how much their total biomass there was in the system, and we're starting to see some nice correlations between our unburned, low, moderate, and high burns and the type of vegetation. So this is percent conifer. So the higher percent conifer, so kind of the more fuel available, the higher the burn severity. So that makes sense. So it's a nice kind of proof of concept that what we're looking at is starting to work. And then we started to use this Ecohydrologic or eco stress product. And so what we're showing here is that all of these different colors, right? So essentially we've got higher ET in our conifer areas, a little bit lower ET in the slopes with the chaparral. But the interesting part for us are these higher ET within the riparian area, and that's the area that's right adjacent to the streams. So helping to kind of control that input of sediment into the system, helping to kind of provide a roughness to the system to slow the water down. And so we think that with this higher resolution, that this is going to help us to, understand the processes and understand whether or not that watershed is more prone to higher fire potential and also to those post-fire flooding conditions. Right, so this one's just kind of showing those images, but showing the histograms. So we looked at kind of one pre-fire image, one post-fire image. That EcoStress product is so new that we actually don't have enough, that much data. So this is kind of more of a proof of concept that we're starting to see the changes in our watershed at the timescales that are of interest to us. And we do so in our control watersheds, the distributions are somewhat similar and the means are similar. However, you can see kind of in the pre-fire burned one, there's kind of, and you'll notice that the Y scales aren't the same here, the 400 versus like the 80. It just means that there's more frequency of a wider range of ET. And then after the fire though, we tend towards the lower end, right? And so this is just kind of an image of some of the recovery after 1 year that kind of correlates to this scene from the Eco Stress product. All right, so ultimately, we're trying to investigate additional parameters that have not been included in the Rogue Countryman and Story and in our machine learning techniques, because we know, there wasn't enough information available to us. So we hypothesize that by contributing, by understanding these vegetation processes and the distribution of them throughout the system, we know that we hypothesize that it's going to contribute to the peak flow, which was a previous limit, which was a limitation in our previous work. So that's kind of why we're investigating this vegetation component further, and how we can kind of incorporate that into our understanding of the landscapes. All right, so I always hate ending up with like, conclusions, because I get excited because there's just so many directions and so much that we can learn. So I'm going to just kind of end with, here's a summary of what we know. We know that fires are naturally occurring, that landscape and water changes after fires. There's this return. It's kind of controlled by how burned it was, what's the vegetation amounts that are present, what's the rainfall like. So it's exciting because there's still a lot of gaps and a lot of work for us to do. And I want to leave you with a few things to think about. That first, there's these natural and anthropogenic disturbances that are increasing across the US. So we're hearing about it all the time: climate, drought, urbanization. So we want to think about, how do we balance the benefits and risks to downstream habitats and communities? And I think it's really critical to apply interdisciplinary tools to understand these extreme events and the impacts. And so there's tons of opportunities for collaboration across the disciplines related to disturbances, water resources, and sustainability issues, hopefully like what I demonstrated today. Okay, and with that, thank you. And I think we're almost out of time, but maybe there's time for a question or two.
Thank you, Alicia. Very nice talk. I think this is a good time for questions for Alicia. Let me get started, maybe, and others will join in. So you mentioned sediment transport and changing of the landscape or your watersheds with the sediment deposits. Wouldn't that have an effect on the change of vegetation in subsequent cycles? And how does that then affect both the watershed itself, but also because now you have anchoring vegetations closer to these watersheds because of the presence of sediments? If you have rocky boulders, nothing's growing on it. I didn't see anything in you mentioned that subsequent changes. How does that work?
It's a good point. So we have done work on that. And so actually we find that in more natural systems, we've done this in the Santa Monica Mountains, a little bit less disturbed and less downstream assets at risk. So a nicer science experiment. But that after the fire event, there's the storm events, and it only takes maybe a few storm events of relatively good size to kind of flush that fine sediments out of the system. It starts to return back to normal. Now this changes with droughts. So in that example that I showed you, the reason why it's taking so long for the system to come back to its rocky state is because there was no rain that year. It was like one baby tiny little rainfall event in like 2014. So it doesn't take too long actually naturally to flush itself out of the system, and eventually it's supposed to make its way to the coast, right? So there's it's really important for that to actually move through the system and not settle in.
Okay. Mm-hmm. And I think you kind of addressed the second question I had, which is year after year, if you're going to have these drought cycles, how does that change the vegetation itself? Because typically we assume 2 years is enough to get the chaparral vegetation back, but your pine forests are not coming back for 20 years. So
no.
that mix is changing.
I completely agree. I mean, I think with, these drought cycles and things like that, it's going to change the fuel compositions. And, we actually have an expert in the room here who could tell you all about like herbaceous grasses and different types of vegetation. She just made a funny face at me. But yeah, no, it's definitely an avenue of research too, in terms of like what's coming back after the fires and how those different patterns also impact the fire patterns too, right? Different vegetations burn at different intensities and have different fuel loads.
I'm going to wait off to ask any further questions to see if there's questions from the audience.
Apparently not.
Okay. If not, then I can ask my question. Forgive me for asking this question because this annoys some people when I ask them this. So there are natural interventions you can do, right? You want vegetation to recover and things. Are there unnatural, meaning engineered interventions, or people call it biomimetic, right? Mimic nature by, so basically you want things that sediment transport or flush out transmit. What interventions, if any, have they looked at for these kinds of things? Or is that a no, that is, you don't want to go and interfere with nature?
No, are you kidding? It happens all the time. So let me show you this image down here. So when I was in Colorado, actually, I don't know, I didn't look into it as much, but they were really concerned that when I moved, I hope it wasn't me, but when I moved there for my postdoc, there was the Waldo Canyon fire, which was, one of the largest on their record for a while. And they were scared about what was going to happen. So you can see this engineered, these like big chain linked fences basically that they put up, these debris nets. They put in about 3 of them. It costed like over $1 billion. Despite us telling them like it's a bad idea, because if you put this big net in there, it's doing is it's trapping all of the roughness, all of the boulders and the logs and things that are trying to get flushed out of the system, and downstream the water is just gonna speed up, right? So then their next problem was all of the erosion immediately downstream. So to me, there's certain interventions that are a little bit more heavy-handed that might be less necessary. And then there's other ones that they've put in terms of like some log felled barriers and things like that to kind of help stop some of the erosion a little bit more strategically. But at some point when the hill slopes are so steep or it's so burned, sometimes there's not too much that you can do other than just let it recover naturally. But yeah, I think there's tons of different management techniques out there, including like seeding and hay mulch, where they're dropping grasses and straws onto the surface to try to protect it, and to also help kind of the vegetation grow back.
I think Elena has a question.
Oh. Yes, thank you. I'm looking into how can we remediate the water itself, after a lot of ponds have had a lot of ash debris in neighborhoods and near the wineries and near the, maybe ponds that are used on resorts, all kinds of areas that are near the fires that have been impacted, maybe, and fisheries, and like not just fisheries, but people have a lot of fish in these recreational ponds and stuff. So do you know of any programs or ideas on that, or thoughts on that?
My work is more on like running surface water. So I've done a lot less in terms of like lakes. I would assume that, I think it depends on how big your lake and your ponds are, I suppose. But I know that we tried to look at, after the Rim fire, we looked at like some of the smaller lakes that feed into the Hetch Hetchy reservoir system. And it wasn't as noticeable, like some of the stuff that was coming into it off of the watersheds. It just gets kind of diluted and settles to the bottom. So I think if you cored the sediments, you would find those material. But yeah, I think you need like a substantial burn area just directly dumping that into the lake. In terms of like the ash fallout and things like that, I'm not as familiar with kind of what could be done with that. A lot of skim it all off, I don't know.
Yeah, because I mean, we have a solution to increase the oxygen content of water, and we have a way to, it's oxygenation of the water with using nanobubbles. So it helps, not in a really disastrous situation, but in a mild situation. But it would help prevent the algae growth and from extra nutrients getting in there. And so we're working on other projects similar to that, and also remediating smelly water from what do you call it? The lettuce processing plants and in agriculture. and stuff like that.
That's
So-
cool.
So there, but I was wondering if there's any use for that in any of these
I'm sure there.
wildfire situations.
Oh, I'm sure there is, especially like you said, as they approach like, drinking water supplies and recreational water bodies. I mean, after these events and things, they have to sometimes close it down due to the water quality, right? You don't want people in there hanging out and drinking it and washing their hands in it and fishing in it and things like that, right? So they have to close these areas off a lot. So I'm sure there's interest in that.
Oh, thank you.
Anybody else?
I have a question. I don't know if you maybe reached this, but did you notice like a huge difference in the ecological zones? So say if it was a forest versus chaparral, or one of those zones more susceptible to these like flash floods?
I'm gonna say yes and no. I think it's also a factor not just of the vegetation, but like the slope. So, oftentimes the higher in elevation you get, we're kind of getting more into the headwater, so we're getting a little bit steeper. That's kind of correlated with those more conifer type of vegetation, rather than as you move lower in the elevation, then you've got the chaparral. So I think it's kind of a tricky question. So
Okay, thank you.
So yes, probably. I don't know. We kind of look at it from a watershed approach, so it's oftentimes it can lump the response to. I would have to defer. I'd have to go back and look into that one.
Anybody else? Going once?
I have a question.
Okay.
Oh, hi, Ryoko.
Hi, Alicia. Thank you for a very interesting presentation. And I wonder if your model, either random forest model or regression model, or currently like building eco stress model, can be applied to risk assessment of the flash flood after fire, or how do I say? Are you like planning to expand that model from the several watershed scales to wider like risk mapping kind of model?
So in this project, no, because we were trying to develop tools that could be used just for them to quickly assess any watershed in Southern California that's small enough and burned enough any year after fire. However, in a different project, we will get there. So actually, Krista West, I saw, is on this call. So that's a collaboration that we're doing, the Connecting Wildlands and Communities project. And so she's actually more of the fire expert and the vegetation expert side, and we're looking at the water. And so from that perspective, I think we are interested in looking at deviations from kind of like a baseline condition to, if we run a fire condition, then how at risk that watershed is to the changes. So eventually that is a goal, yeah.
Krista is more looking at the grid data, right? I guess.
So
At the which data, Ryoko?
Grid-based data, whereas Alicia is more looking at watershed data in more watershed scale. Yes. So yeah, I'm definitely interested in how it's gonna go, because I'm trying to compare the watershed scale soil moisture and satellite grid soil moisture. So yeah, interested in scaling program. Yeah, thank you.
it's a hard
It
to solve. Good thing you're on it.
Yeah, thank you.
Well, I guess we're gonna thank Alicia for a very nice talk, and thank you everybody for attending the colloquium, and have a nice weekend.
Thank you for having me, everyone.
Yes. Hello.
Thank